folks, Assalamualaikum. I'm Mohammad Shahriyar, Mitul, and this is one of my videos on basically machine learning. So earlier we did covered about categorical encoding, then monitoring relationship, and we also did talk about or we did learn about basically uh, the techniques like box walks and so on, right? Now, this time we're just going to learn about discretization and this technique. So let's start with it. So what is this discretization? So you can see this is a skewed graph. Although we've learned like how we can use the variable transformation and make it normally distribution or something near that. But sometimes it can happen that we want to make this continuous variable. Like we have this continuous graph. This is a continuous graph because there is no dropping of the data, right? It's totally continuous. And I make it to something, some data basically, which is some interval and basically create a lots of pins and the data will be out there and might be something like normalized. Okay. So discretization is basically the process of transforming continuous variable to discrete variables, okay, by creating a set of contiguous intervals that span the range of the variables values. So discretization is also called binning. So yeah, we can just call it binning. No problem with that. So why we use it? So that we can improve the performance, reduce training time, mitigate the effect of outliers. We'll learn about outliers. Although we have seen that previously, but we'll just talk about the techniques and others and create simpler features. Now, for the performance and training time, it is again very much helpful, but just look into the scenario about this thing, like mitigating outlier effect. For example, assume that this is the graph and there is a point. Basically, there is another data out there. So this data is totally outside this graph, right? If we can create basically if we use this discretization, there's a high chance that these data will be within one of these discrete values. So this is the goal: removing outliers, reduce basically the training time, improve performance, and so on. It totally depends on the training and others as well. But what is the issue with it? There are some limitations. So limitations are basically can also lead to a loss of information. Okay, because it was earlier it was continuous, but this time it is like obviously not continuous at all, right? There are lots of discontinuous values basically. Like for example, by combining values that are strongly associated with different classes into the same bin, the aim of a discretization algorithm is to find the minimal number of intervals without a significant loss of information. So this is what we are looking into. But yeah, practice, if we just look into that, in practice, many discretization procedures require the user to input the number of intervals into which the value will be sorted. The job of algorithm is then to find the cut point of those intervals. Okay, so this is what we do and we'll do here. We'll do this later on. But discretization methods, there are multiple techniques as a whole for unsupervised learning and supervised learning. The techniques do vary. Now the question might come up to you is what is supervised learning and what is unsupervised learning? So we haven't yet talked about those things in our series, but just assume that is supervised learning is basically we will tell the machine learning models like, okay, this is what you need to do, this is what you need to learn. But for unsupervised learning, we don't do that. Okay, so this is what I hope you got my point, right? Now let's look for the techniques for unsupervised learning. You can see equal weight, equal frequency, arbitrary, binarization, or k-means. These are the techniques we can use for unsupervised one. Like obviously discretization method, these are. And for supervised, we can use these three. Let's look for the equal width. Okay. Okay. So these are going to be much more tricky to understand, but if you just look into the graph and the explanation, I hope you will understand. Okay. So this is a graph. Okay. We have some continuous data and others. Okay. Okay, you can see if you just see this and something. Okay, but after that, the transformation, you can see they are not continuous at all. Okay, great. So from this graph, we have some information here. Let's just analyze this information. You can see, if you just first of all look into here, the minimum age is 0. The maximum age is here nearly 80, which is 73. Intervals, we have decided the intervals should be 10. Okay, we can do that. So the width of each interval should be 73 minus 0 by 10, 7/3. So each interval should be nearly 7, right? So 0 to 7, 7 to 14, 14 to 21, and so on. So you can see 7 to 14 or 0 to 7 and 28 to 35. So all have these, the width is basically constant, and which is 7, right? And minus 0, 0, minus 0.001 basically refers to 0, no problem with that. And what it is referring is, assume that we have this X column, and now and using this basically column, we generated these graph. Now, as we have dealt with the width now, and we have created the interval, now these are the intervals. We can, like, the age 13 is basically in between 7 to 13, 14, right? So this is what we have written, and so on and so forth. We can do that for all of these. After that, we'll just, you see, for 7 to 14, we have 13. So yeah, one time. Another, like, for example, here 7 to 14 is once, right? Okay, no problem with that. We might have thousands of data. Assume that. And 7 to 14 is nearly what? It was called nearly 35 times. Okay, so this is one time. We have called this 7 to 40. There might be more, meaning 34 times there. So okay, so this is how we get the frequency, and you can see from 2, 3, 4. This 21 to 28 is the highest, has the highest number of frequency. Okay, here, that's good. Now let's learn about this thing which is called equal frequency discretization. We just learned about equal weight discretization. Now equal frequency. Okay, let's learn about this one. Okay, so if I just want to look into here, let's just take it here. So I just don't want to talk much more about the theoretical aspect. You can pause this one and you can check this out, but I want to show you much more about from the data. So here you can see we already have this kind of thing. So just understand this one. This was the graph, and after that we have this one. How did you come up with this? Okay. Okay, so here in this scenario, we can see that we have, assuming we are setting the number of beans or intervals we'll have. So that is fixed, assuming that. So yeah, the interval is 10 now, and each interval should contain at least, obviously, should contain 10% of the values. Okay, so for 0 to 16, 10% of the values are within 0 to 16. Now keep it in mind that this interval means that there will be, obviously, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 intervals. That is what it is meaning. But the width is not fixed. 0 to 16, in this range, there is 10% of the data covered. That's what we are saying. So for 0 to 16, as a whole, initially we can start with maybe 0 or 10%, and then it will increase to more 10%, that it should go for 20, and so. Okay, so here 0 to 16, it should be 10% of the data that is covered in here. Okay, up and running. But this is basically meaning that sometimes the value was high, low, and so, but 10% of the data is here, 0 to 16. Okay, so we can refer to the 10 to 16, no problem with that. Then 16 to 20, that was like 20% of the data. And then 20 to 22, and 22 to 25, and so on, right? So it is a mistake though. Okay, great. So it increases in that manner. So this time the frequency is fixed, like each time 10% is increasing, 10, right? So it's equal frequency discretization. Great. There's another which is basically arbitrary discretization. It's as you can understand, it's arbitrary in various industries. Like it is common to group variable values in segments that make sense for the business. It's basically we there is no fixed thing. It basically depends on something. Like for example, if you just look into this, so we have income versus people, right? This is a graph, some sort of skewed graph. Now you are a bank guy and you want one thing, that is that you want these the data set to be or the graph to be generated depending on the income set. For example, you are saying 0 to 45,000. You are setting some obviously bins or intervals: 0 to 45,000, 45 to 65,000, 65 to 90,000, 90 to 150k, and bigger than 150k. So depending on that, you can see there are lots of people, almost like 3,000 people. And for 45 to 65k, like almost 3,500 people who incomes within this range. But here, less than 500 people earns more than 150k per year. Okay. So it depends on that. So again, the data, you can see the discretization has been done, but it totally depends on the scenario. Maybe for this income, as you are from the bank, this is what you have done, but it totally depends on the scenario, how you want to do that. Maybe other factors could have been there as well. Okay. There's another thing which is K-means discretization, and this is something K Forest and others, if you have learned about that thing. Okay. The machine learning technique. Depending on that, you can basically cluster those. So for example, here we have like 0 to 4, 0, 20, 40, 60, 80. So we have here almost 5 centroids. And when we will talk about the machine learning model, you will learn this thing much more better. But I'm just trying to keep this as a black box. You can learn this, you can pause this, you can learn this, but I hope you learn that better when I will talk about that model basically. So you can see from this age, depending on this 5 centroid, we have divided them to 0, 1, 2, 3, 4. Now you may ask like, okay, how did we create 0, 1, 2, 3, 4 from 0, 20, 40, 60, 80? So it totally, basically, we have assigned 0 to 0, 20 to 1 and others. This is how we have done that. So this technique is another thing, which is for discretization with decision trees. So here you can see that how we can basically look into this factor. So assume that you have basically age, right? Age of people. So okay, so assume that you have some people, 1,000 people who are between 0 to 15, then 2,000 people who are between 15 to 25, then 3,300 between 25 to 50, and then 6,000 between 50 to 75. Okay, so when we're dealing with 25 to 50 and 50 to 75, we can easily say that if we have a question, if a person's age is actually more than 50 or less than 50, so you can see more than 50 is here and less than 50 is here. If the person's age is between 50, obviously more than 15 or less than 15, so the question comes up here again. And from 15, from these two questions again, this question can come up. So decision tree is something we haven't learned yet, but using decision tree again, you can see divide these things. Like you can see now there is some there are 1,000 people between 0 to 15, 2,000 from 15 to 25. This again isn't this the same thing we have done? Like we have the range and we have the frequency. Yeah, this is what we have done. So discretization can be done using decision tree as well, but just assume that we are ignoring the decision tree concept much. We're ignoring that for now because we'll talk about this concept in depth later on. So just you can understand why we have called it decision tree, because you can understand if you are not familiar with decision trees. Decision tree is basically like this is a dot, right? So someone will ask basically, okay, if it is yes or no. So there is something, a branch for yes and branch for no. And again, for this, there will be some question and it will go on and go on and go on. So we are making decision and we are creating some branches. And branches are where? Branches are basically in trees, right? Okay, so here you can see there is an interesting thing, that is we have these h and some frequencies in y. X basically in h is in x-axis, and something in y. So after the discretization, what you can see is 0, 0 0.1, 2, 0 0.2, 0 0.3 and others. You have seen that earlier as well, how we can come up with this thing. So you can assume this just like 0 to 0, 20 has been assigned as 0, 20, 40 has been assigned as 1, 40 to 60 has been assigned to 2, 60 to 80 has been assigned to 3. And using some lot of techniques like maybe min-max or others, we can convert these to like 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4, okay. Okay, that should be enough for this, and you have converted this. Now, the question is, into the y-axis, we have 0, 20, 40, 60. How did you convert to this to 0 0.3, 0 0.35, and so on? Same techniques used here. We're just keeping them as black box. We're just focusing on the relationship. After discretization, you can see that there was no proper relationship mentioned here. You can see this was the graph. And now it increased here and it increased here. So after the conversion, monotonic relationship, you can find it monotonic relationship. It has been increasing, not totally linear, but uh, kind of linear. But you can't say that totally linear. So here, there are some example for you. If you are not familiar with the monotonic relationship, which we have covered into our last video, so you can see that this is the x and this is the y. As x increased and y increased, okay, the graph is increasing. But there is no linear relationship, but here it is decreasing, but there is a total linear increasing. But this is not monotonic, because you can see increasing, decreasing, and so on, right? These are not monotonic relationship, these two. So yeah, that is it for your review for the monotonic relationship. So let's look into the codes for discretization. So using the k-means, which we learned at the last. So here, for the age graph, this is the graph. For the fair, this is the one. You can see this is kind of into the normal distribution, and this is almost skewed. So after that, you can see the age has been converted to this, and the fair has been converted to this. So you can do that for sure. The decision tree. I'm not talking or explaining the codes line by line, because so far we have gone through each of the lines. We have explained that, and assuming that you have gone through those and you have learned those. So now I'm just going to show you like how this thing is working, what it is, and if you have any query, we have Copilot out there. You can ask the questions. You can ask the question in the comment section as well. There's no problem with that. But surely go through that. There are lots of places where this explanation will be much more better. And I've already gone through these explanations, loading the data up. Then obviously we are calling the libraries and so on, right? The monitoring relationship between the age and target. So this is what that has already been generated out there. So yeah, there's a relationship that's good. There's also binarization. Okay, binarization. So here you can see these are where yeah, right. For the binarization, this you can see 0. In binary we have 0 and 1, right? So this time we have just 2, right? You can see these and these, those or these, or this or this, and so on. Right. Again, this is part of discretization. So you can just look into them. So the repository will be provided, so you can just look into them. Especially I would suggest to go for this discretization, okay, equal with discretization and equal frequency discretization. So if you just look into that, you'll see equal width, right? So the width should be same, whatever the frequency is. So this is before, was after, this is the after. You can see the frequencies are something that is not fixed, but the width is fixed. That's great. And this is for the fair, and this is for the age. Interestingly, for here you can see for training data set, these were the blue, So the test in test the frequency is higher. Sometimes in train it is higher, the test is lower. Great, but it works good for the fair data set, so it's good. Equal frequency. Okay. For the before, and let's go for the after. So yeah, this is something, and you can see that compared to the equal width, here we have lots of obviously bins or intervals, you can see, and almost the frequencies are kind of same, but yeah, there are lots of bins right now, you can see. And here specifically you can see it was not like that, but here the frequencies are kind of same. So yeah, that's what we've gone through. Okay, now we've gone through discretization. I will now learn about the outliers. So let's move on. Okay, so what are basically the outliers? So outliers are basically like in a graph. If you have any input which is not within the graph or the distribution, we consider them as outliers as a whole. So an outlier is a data point which is significantly different from the remaining data. That means if the remaining data, like there's lots of data which follows some sort of pattern and so, and there is a new data which comes up and which is totally outside of the pattern, this is considered as outlier. So how we can work with the outliers? We can trim the data set, we shorten them, so the outlier is gone. We can work with the missing data, so we can do that. Treat outliers as missing data, okay? Or discretization, we can do that. We have also you have also seen that how that works with here. See outlier, and once we gone through the discretization, and that was solved. And censoring, which we can use capping, top or bottom coding, or winsorization. Okay, so this is what we can do. Let's now go for the coding portion and see if we can do some kind of thing. Okay, so removing outliers. We have just two here, basically capping and removing outliers, another one. So here we can see that this is the box plot histogram, and okay, the loss of data, like the majority of the data are here. If you just compare these two data sets, you will understand what's happening. There's a majority of the data are nearly here within this region. So that is the box plot shows, okay, majority of the data is here. But after this range, there are lots of outliers out here. You can see the lots of data which does not belong to this majority of the data. So great. So we have already talked about this interquartile range, and so using that, okay. So you can see that the black dots outside the limit, these are outliers. So can we solve them? Can we remove them? Can we solve the issue? Okay, using this technique, okay, quantiles, interquantile distance, we have already talked about that. Using this, if you just go through that, now you can see after this technique, no more outliers is present here. So, okay, this explanation, the coding is something you can look into, but we have already gone through this topic earlier, this interquartile, basically quartile range, right? So, yeah, I hope that will help you understand why that we have gone through these 0.05 and 0.95 and others, okay? Let's move on to the capping outliers. What is this capping or censoring outliers? We've just learned about the top term, but we haven't seen what we do. So we basically calculate those using basically, you can see the caps using basically the normal distribution, IQR proximity rule, and the quantiles. Okay. So here again, you can see that there are some data which are outside this thing. Some data here, some data here. We can use normal distribution to cap them. After that, it's better. But after outside that, we use IQR again. Using IQR, you can see there are no outliers out there, so that's very good. You can use quantile here as well. So it's again very good. But for the earlier one, for the removing outliers, you can see for the quantile. Basically, it worked perfectly, but for again, for the normal distribution, how it worked was there were lots of outliers out there still. It was not resolved though. But again, when we use this one, basically IQF, again, there are lots of outliers out there. But it's good that when we use the capping, for the capping one, it was resolved for this quantile. It was again resolved for this one, normal distribution, and sorry, IQR, and it was again solved for the normal distribution. Great. So the techniques we can use, sometimes it will work, sometimes it don't. So we have options in hand, we can just test them. So in both cases I have seen, just you can see quantile was the better one, which could resolve the outliers, but sometimes it might not. This can also happen. Okay, so let's move into date and time variables. Okay, then we'll go for mixed variables, and we are almost near to our end of the feature engine topics, although we have feature scaling left as well. Okay, so date and time variables. So there are sometimes we will have variables which you can see have date and time basically as a whole. You can see date of birth, which we have numbers only. For date of application here, we have numbers and strings as well. And for time of accident, we have only the numbers. For mixed variables, if you just look into here, for in case of mixed variables, what we have here is number or labels in different observation, numbers and labels in the same observation. We can have that. So what are we referring to mixed variables? So here you can see 0, 1, 0A, 3D, 0. So we have numbers, we have strings, everything in the same column. Okay. We can now from this column we can create two columns. One will have only the numbers, one will have only the categorical values. So here CAT means the categorical values or strings. So 0 refers to number, right? So there will be number. Is it referring to any categorical values? No. So that means not an N. Which is here for not a number, something like that. For 1 is here. But talking about A, you can see A is a categorical value, which is here. Is it a number? No. N. So this is how we can do that. So for the mixed variables, this is how what we can handle. And for example, here for the basically the Titanic dataset, we had this cabin and so on. You can see A01, which can be converted to A, and 01 here. Great. Now let's move into the code and see. Okay, into the date time features, you can see extracting date related features. Again, it's going to be simple Python stuffs. We'll just use this kind of things here. You can see loading the libraries, install this, open PyExcel using this dataset online retail 2. So there are lots of columns which we have taken. The types of this one. Time. Okay, so here you can see this is one of the examples: year, month, and date, right? Great. So date time object. So here you can see also the time. So you can extract the features, obviously extract the date, year, and others, right? So here you can see using this technique, what we can get is from this one, we have extracted the year, right? Great, no problem with that. In the same way, we can extract other information as well. That is it. So year, start and end. We can also look into lots of information. Inverse year start, inverse year end. So you basically this notebook is basically created so that you can work or play with the date time here, right? So you can look into that. That's going to be easy for you. And yeah, nothing new that much. Basically working with the data, specifically day of the year. So here inverse day year, it was 335 for all of the informations here. 335. Great. Okay, Let's move into the extracting time related features. That was totally date out there earlier. Now it's for the time. The data, same data set, date was this, inverse date. Okay. See, when did we extracted this one? Work with different time zones. Okay. Okay. So here you can see is basically as we are dealing with the time. So from this data, converted these to UTC. It was UTC plus 2. And it is converted UTC, and it is the time for London. So you have some data and you can convert this to specific zone or something. You can do that. Although now you can ask, why are we even bothering? As this is not a very difficult topic to discuss, and that's why I'm just skipping these topics. I'm just going through that so that you can go through the basically notebook later on and take your time. But it's simply just basically you have some data, you're doing some pre-processing techniques, that's it. And now why are we doing the pre-processing? It totally depends on the context. We don't have any context right now because we're not creating any project, just talking about the basic stuffs. Okay. So yeah, now let's move to the mixed variables. Mixed variable, we have just one. Here you can see. Okay. So this dataset, sample S2 CSV, it has basically lots of obviously numerical IDs and some categorical and numerical values. Now you can ask why or how. Again, you can just go to dataset and I believe sample 2, right? Yeah, sample 2. You can go for that, but surely not from here, from VS Code. Just go from your computer and then check this CSV file. You will see that you have lots of numbers there, some categorical values and some numerical values. Now it is important to understand that within the same column, if we have both of the things like numerical and categorical, sometimes it's going to be difficult, right? It's going to be difficult to understand what it is meaning. That's why what we can do is we can convert this column to two new columns, right? One will be for numbers, one will be for the categorical values. Exactly, this is what we are going to do, and has been done. You can see, like for this value, the categorical value was C, but the numerical value is 0. Now, how do we verify that? We can surely go to the Excel, but just you can see, each into the column we had either a categorical value or a number. As we have C, that means a categorical value. There is no number. That means number should be 0. That is how it works. Okay. Great. So, or now you can look into this. This was only the numerical one was generated here, but this time 2 were generated. So you can see for C, we have the categorical value C, but numerical value is nil. For A, the categorical value is A, but the numerical value is nil, right? This is how things to work. So yeah, that's good. Yes, we have gone through a lot. We just have two important one, which is feature scaling, one of the most important portions, and another one is the pipeline. We'll just understand how things work. All of the things we've covered so far, we'll just talk about it, and if we're ready, then pass it to the models. Okay, now let's move to the concept. Okay, so one of the most interesting topics, basically feature scaling. Sometimes people do refer feature engineering and feature scaling as same, which is not. So feature scaling. So assume that you have 100 taka note, right? You 100 taka note, and you have just given this is Eid al-Fitr, okay? So there is something called a salami, right? So people do, go to your home and they will meet you and they will have the person some salami, right? So assume that you have a bundle of 100 and you have given 100 taka note to one of your juniors and 100 taka notes to another. So let's just understand 100 taka. So 10 notes, 20 notes, 30 notes, 40 notes, and so on. Okay. Okay, it can happen. What if we divide every value by 10. So it is now 1, 2, 3, 4. Okay, we know that we have divided that. The significance has not changed, right? Because you know you have provided the most to this student, right? But it is better now for the machine learning models because the numbers are less, so it will take less time to compute. These are one of the things we need to deal. Basically, you can see there are machine learning models which are affected by the magnitude of the feature. If the magnitude or the amount is very high, it is impacted. That's why for linear and logistic regression, neural network, support vector, SVM, KNN, k-means clustering, which I was referring to the k-means and others, LD, MPC and others, while we are doing that, we need to go for the feature scaling. But in case we have classification and regression trees, random forest, gradient boosted trees, we don't need that. Okay. So what is this feature scaling? Let's learn about feature scaling as a whole, but okay. Feature scaling is the process of adjusting values measured on different scales to a common scale. Okay. Let's make it easier. As I said earlier, we had 100, we had 10, 20, 30, 40. Then we made it to easier something, which is 1, 2, 3, 4. Scaling, feature scaling, or like we have decreased, but it's not scaling, but again, decreasing is a scaling as a whole, right? So there are some techniques of feature scaling. Let's just look into that and you'll understand. Earlier, we have done what? Variable transformation, right? Transformation, right? When we did the variable transformation, I hope you understand or remember that we changed the distribution of the graph. The graph was earlier like some sort of skewed graph, but after that we turned it to some normal distribution graph, okay, using the variable transformation. But when we're using feature scaling, it is not that. It basically remains what it is. So for example, here you can see the graph was something like skewed, but it is the same. That means using the feature scaling techniques, not only about the standardization, it is not about standardization. There are other techniques, right? Okay, standardization is one technique, min max is another technique. If you follow any other techniques, basically within feature scaling, it won't change the graph distribution. It won't change the distribution. That is why we do the feature scaling. Because remember, variable transformation is something we have learned earlier. So if we want to change, we have already changed that. We have already gone through that. After that, we are doing this feature scaling just to minimize the huge magnitude to some. We are basically trying to minimize those magnitude, right? So that the model can learn very well. That's the reason. That's why we don't want to change the distribution of the graph. That's so feature scaling. In feature scaling, the distribution of the graph is not changed. That's very important. Okay, great. So if you just look into this, so min max for robust scaling, you can see again the graphs are not changed or hasn't changed, so you can call it 3. And but if you have to change so the graphs or distribution of the graph, basically what you have to do is surely you need to use this variable transformation. Okay, now the laws are given here. The formula basically standardization. For standardization, you can just look into the example. For example, this is a column, okay, and here for this column the mean value is 79, the standard deviation is 51. So this is z score, which is the value which we will put here. It is basically x, a particular value which is maybe 100 minus mean 79, 100 minus 79 by standard deviation, which should be 51, and we will get this 0.41. And this is what we do. Now, interestingly, if you just look into the graph, this is the interesting one. Earlier, that whole column had, like you can see, the mean was 79 and others. Standard deviation was 51 and so. After the obviously standardization, the mean is now nearly 0, which is very important. Now you can say why and how. Let's just look into here. You can see most of the value, you can 0.41, which is obviously greater than 0. greater than 0, less than 0, less than 0, less than 0, greater than 0, less than 0, less than 0, greater than 0, less than 0, greater than 0, right? Very near. So, and these are all very much near to obviously 0 to 1 and very much near to 0 now compared to the previous one, which we had like mean 79, mean 51. If you just want to find the mean, you can easily now find the one. You'll see it is very much near. So this is the graph how it should look near the 0 mean. Basically, most of the 50% of the data not in 0, obviously not in 0, obviously near 0. 50% of the data should be near here, and this is basically exactly this is the graph of normal distribution in general. Okay, great. For mean max scaling, again this is the law, and this is how we can do it. Here you can see the maximum value is 200, minimum is 20, range is basically minus this 180. So observation like 100. So here it should be 100 minus minimum, which is what 20 by the range, which is 180. So this should be 0.44. Great. Again, you can see the minimum and maximum values are within 0 to 1. So minimum maximum is within 0 to 1. You can see is very much interesting, right? The minimum should be 0 or bigger than 0 or something, but the maximum should be 1. That's good. Okay, the mean varies, variances varies, preserve outliers. That's good. That means outliers is still there, preserves them. Then mean normalization, max absolute scaling, lots of techniques for mean normalization, a particular value, and then the mean minus mean, then the range. You get it. This basically centers the mean at 0, and the mean and maximum is within -1 to 1. That's good. Variance varies and preserves outliers. Good. Mean not centered this time. Here mean is not centered. Okay, so it's not like the normal distribution. You won't see that. Great. Now robust scaling is basically we have a particular value, then minus median, and then IQR, which we have learned so far as well. So the median centered at 0, that's good. Not mean, it's median. Handles outliers. Okay. Earlier we had seen preserves outliers, but this time this robust scaling basically handles outliers. That's good. Okay. Now let's talk about this process. We have gone through a lot. Yeah, great. Okay, I've gone through a lot. We have data, which is kind of .csv in CSV format or Excel. Not Excel basically, it's just to make it easy for you. The Excel files we've seen in .csv format, this is the data. We've analyzed the data. Then we have done the feature engineering. So this video is also part of feature engineering. We have done imputation, we have done lots of very category encoding, we have gone through discretization, we have gone through a lot, right? So we'll do that. Then we'll choose the variable which we'll use in X and which we will use in Y, and then we'll pass it to the model. Once we got the result, we'll deploy into the production. That means it will be up and running for the users. Great. So we have got for the feature engineering specifically, you have seen we have extracted features from dates, features. We have extracted from mixed variables. We have worked with data imputation, missing data imputation, categorical variable. We have worked with them. Numerical variable transformation, discretization, outlier handling, feature scaling, and more. We've learned lots of topics. Those are going to be there out there into the GitHub repository. You can just download them and use the Copilot to learn much more. Okay, don't worry about it. If you haven't understood any code, Copilot is out there. But you can also reach out to me and ask other questions. Okay, why we did this? Ask in the comment section as well. Right now, we will talk about the pipeline. The last, but not the least. Okay, so this is a pipeline. What is a pipeline? Pipeline basically means in a pipe, you see if the water flows, right? Like pipe, if the water flows, it go from here to here, here, and then goes from here, right? So things are ready. It basically 1, 2, 3, 4, like, like this is 1, this is 2, this is 3, 4, 5, right? 1, 2, 3, 4. All of the droplets are there, right? So it will fall then. So into the pipeline, what basically we're meaning is, we need to create a pipeline or create something so that it can handle all of the process we've done. So just look into here, pipeline steps for training. So if there is any missing data, we should use imputation, right? So imputer is here. Then for the categorical value, we should use one-hot encoder or any other. So you can use categorical encoder. Then discretizer, we can use that for discretization. We have learned that we can use that. It depends on the scenario. And for the quantile one, you have seen using the quantile one, the outliers was very much less. That means we have handled we have handled the outlier issue using quantile one. So yeah, we can use this strategy. And then we can use the feature scaling. Here the standard scaling has been used. That is standardization, right? So then these were created, then they were called, they were used. You can see that as I mentioned, we have a data and we've split the data into training and split the data into test. This training has X and Y. So you can see X train. For the X data, they have first of all called this imputer and filled the missing data. Done. Then for the categorical values, it used the categorical encoding. Then discretizer, it used that, and then feature scales it used the standardization. Then they used this gradient boosting classifier, this ML model. Okay, that's it. And yeah, after that it was trained properly. Okay, great. Then as the training has been done for the model, the testing can be done. So the same thing was done here. You can see imputer and others done, and then started to find out the Y predicted. Y predict. I have already mentioned in my last video, X train. I have talked about X train, Y train, X test, Y test, and Y predict. Okay. Using this, we trained the ML model, and after that, using X test, we try to find out Y predict, and then we compare Y test and Y predict to find out the accuracy of the model. That is the basic one. If you're totally completely beginner for the ML stuff, this is what you need to understand. Great. And using scikit-learn and others, you can easily just, rather than writing these lines, you can easily create a pipeline. You can see there's a pipeline, and after that you can see imputation was done, encoding, categorical encoding, which was one-hot encoder, discretization is there, feature scaling is there, and then the model is there. That means using the scikit-learn pipeline, basically library, you can totally mention each and every droplets just like that. 1, 2, 3, 4, 5. You can see it is 1, this is 2, this is 3, this is 4, this is 5. Everything I mentioned, whatever you need to use, it will just do that. Then you will just easily do the training, and then using the test data set, you will predict, and then pipeline will predict new data. You can also look into the new data. So yeah, we have gone through, you can see prediction, others. I hope if you have understood, and scikit-learn data. It has lots of basically techniques, specifically like imputation, categorical variable encoding, discretization. These are the libraries it has, so we can use them. Okay, you can use other libraries. So let's look for the coding portion, and yeah, let's go for that. Okay, so here you can see for standardization, same. It should be basically nothing like you see after the standardization. There should be no difference, and you can see skewed as well. So it's basically, you can just look into them, no problem. It's basically the different feature scaling techniques are out there. Here you can just go there and look into if there is any change to the distribution of the data for features, mean normalization, maximum absolute scaling, robust scaling. Let's look into the robust scaling as it handles the with outliers. Let's see the graph. Okay, the same, right? Yeah, great. and length. It's not important. Yeah, let's look for the pipeline. Okay, what is this pipeline, right? So pipeline basically, as I mentioned, the steps, right? So we have got actually called all of the libraries here, called the columns here. Great. Then we have discrete variables, continuous, mixed, and categorical. There are lots of the stuffs we have. You can also check out the outliers here as well. Okay, missing data. Okay, so we're starting with missing data imputation. We've done that. Great. Then categorical encoding. Okay. Then discretization. Great. Then we will put all of the things together and create the pipeline. You can see and mention all of the things, and it should be good to go. This is the basically the last one. And interestingly, we have a result out here. You can see relation between survival and other columns. I have already mentioned, because we have already gone through the Titanic dataset for a longer period of time. So this time again, you can see this is basically the survival one, and this is these are basically the other columns we have. So the sixth column has the highest number of relationship with the survival one. That means if there is a male, there's a high chance he is alive, or if there is female, there is a high chance that the person is not alive. It totally depends on the data. We need to look into that, but keep it in mind that there is a almost 86.9, which is 87% accuracy for the training set, and there was 82.5. That is good, pretty much good. But keep it in mind, we have used imputation, we have used categorical encoding here, we have then went through a lot of the stuffs, right? Real level encoding, here you can see ordinal encoding. You can just use all of the stuffs. Okay, great. Regression house prices. So this was for the Titanic one, and this is for the house price prediction. So you can see the house price is same thing. Again, you can also see there is no monotonic relationship out here. That's sad. Variables, continuous variables, missing values. We can work with this one, missing values, and then outliers handling. Okay. Outliers, discrete variables. Okay. Monotonicity, basically finding the relationship here. Okay. Variables, cardinality. Great. Separate train and test. Okay. Variables, missing data impression. Okay. Okay, great. So yeah, again, this was this random first one, which we'll learn. Sorry, my bad. Regression, which we'll learn later on. But yeah, you can see it's kind of, yeah, as it's increasing, it's also increasing. That's good. And also see for the garage cars, it has the, obviously, this was the most significant column. Depending on that, we can say, okay, there's a very good connection if the garage, the number of cars maybe into the garage like 7. So there will be very high house price. And if the garage cars are very, like there's no garage cars capacity there, the price might be very low. So this is what we learned from this model. I haven't gone through each and every coding line because we have seen these so far, right? So that's why I'm just skipping that only for this one. Let's just look into this one. We'll take our time now. We'll take our time and do the cross validation. Okay, let's just run this one. Great. Running this one, let's just go line by line as we are ending our featured engineering series. Okay, so all of the libraries are out there. Then from the Titanic dataset, we're calling 1, 2, 3, 4, 5, 6, 7, 8, and 9 columns, where this is Y and others 8 are X for cabin variable. Okay, what I'm going to do right now is basically, I'm also going to open the data sheet. Okay, data set basically. Okay, let's look into the data set. Basically, here you can see that we have P class, survived, name, 6, age, and so on, right? We have almost 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right, 14 columns. But within that, we have just chosen 9, right? Okay, we'll just open up once it's needed. So for cabin variable, which is, if you just look into here, cabin, you can see B5, C22, C22. So it has mixed variables, right? Great. So we can just work on it and you can see data cabin, stored, extract, D plus, captures the numerical part here, D plus, and for the float and others, and captures the first letter here, 0, first index. So it captures these ones like the categories, and there is another for the numerical portion. Make list of variable types. We're trying to look for how many different types of columns we have. You can see there are 3 discrete variables, 3 continuous variables, 3 categorical variables. Okay, great. We have how many? If you just split the data, like here you can see test site is 0.1, which we encourage to be 0.2, 80, 20, but here it is 90 and 10%, which is not that good though. We can just convert this to 20. Control S, run all. Okay, it's better now. 1047 and then 262. Set up the pipeline. Okay. Into the pipeline, first of all, we are handling with the missing data. Okay. Imputer for the basically for the numerical one, we will handle in a way. For the categorical one, we'll handle in a way. Okay. For the numerical one, we're using arbitrary number. We'll use arbitrary number. If there is missing data, we'll just use any arbitrary number out there. And what is the arbitrary number? We have just also assigned that to -1. Great. For the imputer, for the categorical one, you can see we'll handle this for these variables. Okay. And then after the imputation, we'll handle the encoding, which is for the categorical data encoding. Great. And then that should be good to go. Then okay, we'll use the gradient boosting if others are not needed, right? Also, there is an interesting thing which you have seen so far, that is you can try different value or variables or different things, right? For the imputation, if you just look into this numerical one, we assign -1, but assume that you have a desire to test this model with different ones. So here you can see -1 to 99, you can use 99 as well. So just providing these values to this model and saying, okay, test everything. So even for the real level encoders, it can be 0.1 to 0.2. Categorical encoding, you want to look for the ordered or arbitrary one. So ordered encoding, categorical encoding, or arbitrary one. You want to test different ones. So you can do that. This param grid is something which will test these things for you. We'll try different combinations and others for you. Okay, so yeah, you can see arbitrary number imputation, categorical imputer, yeah, level encoding, ordinary encoding, and others. We have gone through that. You can use that. And after that, after it's running, you can see that again, this variable, 6 variable, was basically on column had the high number of basically connection with our target one, which is basically the survival one, right? Again, using this classification, when we use the classification, it was the same. And for this pipeline, again, it was the same, because here we are using this GBM basically as a whole. All right. Gradient boosting classifier. And here, what did we use? We use gradient boosting classifier. So yeah, that's why that is also the same. But there is no guarantee that if you use the other one, the result will be changed, right? But as a whole, you have seen a lot of stuffs, but this time in classification and this time in regression, we have just gone through how we deal with classification in a dataset called Titanic dataset, how we deal with the regression on using for the house price dataset. And that was basically into this pipeline with cross validation. Cross validation was basically meant because, or said because, we are trying to learn, or we are trying to use much more techniques. Like for example, if we just come up here, you have already seen, like when we are doing the imputation and others. Earlier for the numerical imputation, we wanted to use -1, but later on we wanted to using this one, like the grid and the cross validation strategy. We also said we want, if you want, you can also try with 99 and others. If for category encoding, you can use ordered and arbitrary, whatever suits. You can just try, and it did try, and it found out the accuracy. Like you can see, based ROC from the grid search is 93.6%. But for the classification here, we just mentioned exactly what we want to do, and the ROC was basically here, I believe 86 or something around. Yes, what is that? Yeah, 86, right? So yeah, we tried various combinations and permutation combinations, and then use that model, and into the cross validation. It's better if you are not sure about some techniques, use the cross validation. You will see, like it will use multiple. You have to obviously provide the options, and then it will be good to go. So yeah, that is it, and the data set is basically here. So this whole repository link will be provided to you into the description section. So thank you so much for watching this video. And if you have any questions, suggestions, and others, feel free to DM that in my LinkedIn, or you can also feel free to share this video with the juniors who are learning basic machine learning. Okay. Although I had to skip a lot of the notebooks because I've already covered that in my earlier videos line by line. So this time, if I want to cover all of them line by line, it will take lots of time. So which I don't want, and I hope you will have this. You will use this Copilot if you are stuck, ChatGPT, Gemini, and so on. Or you can reach out to me as well. So thank you so much for watching this video, and see you in the next video.